Hi friends, in this video we are going to discuss about one important concept, that is functional dependence and functional independence. So here first I want to discuss about matrix. So for example, here for example, let's say this is my matrix A and the matrix A of order, let's say m cross m. So this is my matrix A of order m cross m, and let's say the rank of this matrix is full, let's say m. So if the rank of my matrix is m, then I can say so determinant of this matrix which is non-zero. Here A is the matrix of order m cross m and rank of A is m. What is meant by rank of A equal to m? So this rank of your matrix, that is m, indicates in my matrix number of linearly independent row are m, means no row is the multiple of other row. That means m row in this matrix are linearly independent. Means what is meant by linearly independent row? Just linearly independent vector means all the vectors, all the m vector in my matrix A have different direction. So for example, let's say this is my x vector. So here let's say x axis is my x vector and let's say y axis is my another vector. So here this is one vector. Here this vector is linearly independent to this vector y. Means there is a, this is the, let's say here I will denote this as here m comma 0, and let's say I will denote this as 0 comma n. So this is my m comma 0 vector, and let's say this is my 0 comma n vector. These two vectors are linearly independent, means the direction of this vector is different from direction of this vector. Means there is a, means this vector is having different direction and this vector having different direction, means these two vector x and y are linearly independent. So linearly independent vector have different direction, and let's say dependent vector, let's say this is my x axis m comma 0. So let's say this is my one vector a1 equal to m comma 0, and let's say here I am defining a2 as here 2 times here m comma 0. So my vector a2 is the, here this a1 and this is a2. So here a1 is my vector m comma 0 and this a2 is my vector 2 times m comma 0. Can I write a2 as 2 times a1? So here in the same way, if 2 is non-zero, a1 can be written as 1 by 2 times a2. So here this is my linearly dependent vector, means one vector is the multiple of other vector, means the direction of one vector is same as the, means direction of two vectors are same. Just scaling by, here this a2 is the scaling by 2 and this a1 is the, means this is extraction. So here this is expansion with respect to this 2 and this is contraction with respect to this 2, the relation between these two vectors. So here these two vectors are linearly dependent, and this here these two vectors are linearly dependent a1 and a2, and this x and y are linearly independent vector. Means here in case of matrix, when you are saying the rank of my matrix is m, at that time you are just whenever you are saying the rank of my matrix is m, at that time you are saying my matrix m have m linearly independent vector or m linearly independent direction. So here, so rank of your matrix A is m and m is, A is the matrix of order m cross m. At that time you can say my determinant of my matrix is non-zero. So here if A is the matrix of order m cross m and my rank of A is strictly less than m, at that time you can say here determinant of A equal to 0. So here A is the m cross m matrix and rank of your matrix is strictly less than m. This means that either one vector, so here at least one at least two vector, at least two row in your matrix are multiple of each other. So means, so let's say this is your m first row, second row, third row, fourth row up to mth row. So here this is my matrix, here m row and let's say m column. So here 1 2 3 m column. Here this determinant of my matrix is 0, means at least here this two row, row number 2 and row number 3, row number 2 and 3, let's say they are multiple of each other. That is, this means that this vector and this vector are dependent, that is they are having the same direction. So here if all the m row are different, at that time if determine rank of my matrix is m, at that time here I am saying my m row, that is this row, this vector, this vector, this vector have different direction, means they are linearly independent. If rank of my matrix is strictly less than m, that is determinant is, at that time determinant is 0, at that time at least 2, so any of these two vectors, any of these two row are multiple of each other. So here now in the same way I want to define functional dependence and functional independence. So here this is your matrix A, here m cross m matrix. So here this is rank of A equal to m. This implies determinant of your matrix is non-zero and your matrix has m linearly independent row, or we can say vector. Now here this is same, here A is the matrix of order m cross m, rank of A is equal to, let's say, n, which is strictly less than m. In this case determinant of your matrix A is 0, that is here determinant of your matrix is 0, at that time we can say here at least two vector, at least two row in your matrix are multiple of each other. So here this is here m row, so here at least, so some row, here I will write some row or vector are linearly dependent. So here this is m row are linearly independent and some row are linearly dependent. So here means determinant is 0. So in the same way I want to define functional dependence and functional independence. So here functional dependence is related to linearly dependent vector and functional independence related to linearly independent vector. So here functional is nothing but a function. So here what is meant by function? Let's say f of x equal to, let's say here I am defining function f of x equal to y. So here y equal to f of x is my function. So here this function in x variable. So at that time this is my output and this is my input. So input is my variable with respect to this function f. So here in function, whatever the input here you are using, this is again one function. So here let's say f of x equal to something. Let's say here I am defining y. So here functional is a function whose input is again a function. So here this functional is nothing but a function whose input is again one function. So here this is my normal function and this is my functional. So here for this capital F, this is work as an input. So here this input is again one function. At that time we can say this capital F is a functional. Capital F is a functional. Now here I want to define functional dependence and functional independence. Now let's say here I am defining, let's say z equal to u of x comma y. So here, so now z equal to u of x comma y. So here z equal to f of x comma y. So whether this functional is dependent or functional is independent. In the same way here functional, here vectors or row. In case of matrix, a row is nothing but a vector. So if vectors are linearly dependent, so at that time one vector is the multiple of other vector. In the same way, if the functional is dependent, at that time one function is depend on one function is multiple of other function. Here row or vectors are linearly independent. At that time no vector is the multiple of other vector. So if functional is linearly independent, so no function is the multiple of other function. So here in case of Jacobian, so let's say u equal to f of x comma y is a function, and the Jacobian of u comma v with respect to x comma y, which is equal to, so here determinant of ux so here uy vx and this is vy, which is equal to, here this is my determinant, here determinant equal to 0, here determinant equal to 0. At that time your functional, here if determinant of your matrix is 0, some row in your matrix or some vectors are linearly dependent. So here if determinant is 0, your functional is functional dependence. So here if determinant is 0, here functional u comma v, or you can say u comma v. So here u comma v. So here u is again one function and v is again one function. So here u comma v are functional, here functional dependence, functional dependent, or you can say related. So here linearly independent vector are one vector is the multiple of other vector, or we can say functional dependent, or some authors say this is functional related. Now here in the same way, here j equal to, here determinant of this ux, uy, here uy, vx and vy, which is equal to here not 0. So here determinant of your matrix is not 0, at that time linearly independent row or linearly independent vector. So here determinant is not 0, at that time your functions ux, uy, u and v are independent, that is linearly independent, that is functional independence. Therefore here if Jacobian is not 0, then we can say u comma v are functionally, here functionally independent. So here functionally independent. So here just keep one thing in your mind. Here Jacobian is a determinant. Jacobian is defined by determinant of your uxx u comma v with respect to x comma y. If Jacobian, here if Jacobian is non-zero and if Jacobian is 0. If Jacobian is 0, this is dependent function, so functionally dependent. So here functionally dependent, and if Jacobian is non-zero, functionally independent. So here if determinant is 0, some vector are dependent, and if determinant is non-zero, so here if determinant is 0, so here vectors are dependent. If determinant is non-zero, vectors are linearly independent. So in the same way, here determinant, here this is related to this. Here Jacobian is non-zero, function is functionally independent. Here if Jacobian is 0, here determinant is 0, then if Jacobian is 0, at that time your function is functionally dependent. Here linearly dependent, here functionally dependent, here linearly independent, here functionally independent. So this is the concept of functionally dependence and functional independence. So here functional dependence is related to linearly dependent vector, and functional independentness related to linearly independent vector. So here this is the concept of functional dependence and functional independence. So here now I want to discuss some problem, so you will get one clear cut idea. Now, so here I will discuss just first I will discuss just normal problem. Let's say here I am defining one function u equal to, let's say x, and let's say u equal to x and v equal to y. So here just observe one thing, u equal to x is my x axis and v equal to y is my y axis, just for the sake of understanding. So here I want to define, here I want to check these two functions, u of x comma y equal to x and v of x comma y equal to y. They are functionally dependent or independent. So here let's say this is my x axis and this is my y axis. So here Jacobian, so here geometrically just observe, this is x and this is, here let's say this is y. So here they are not multiple of each other. So here Jacobian of u comma v, so here j equal to with respect to x comma y, which is equal to ux and uy, this is vx and vy, which is equal to, now here how to find ux, partial derivative of u with respect to x. So partial derivative of u with respect to x is here 1, partial derivative of u with respect to y is 0, partial derivative of here v with respect to x is 0, and partial derivative of v with respect to y is, let's say, here 1. Therefore Jacobian equal to, so here Jacobian equal to defined as u comma v with respect to x comma y, which is equal to, so here ux is 1, uy is 0 and vx is 0 and vy is 1, which is equal to 1 minus 0, which is equal to 1. Therefore, this function, that is u here, this is nothing but u of x comma y equal to x and v of x comma y which is equal to y. So therefore, these two function here, u of x comma y and v of x comma y are functionally independent, because here determinant is not zero, which is equal to not zero. Therefore u of x comma y and v of x comma y are functionally here we can say independent. Here independent. Now this is the example of functionally independent. Now here I want to define one function which is here now. So here this is functionally independence. Now here I will define one more function. So now let's say here I am defining one function. Here let's say second function, u of x comma y equal to, let's say, x plus y and v of x comma y equal to 2 times x plus 2 times y. Now I want to check whether this functions, that is whether this function u of x comma y and v of x comma y are functionally dependent or functionally independent. So here this is given thing. Now we have to find j equal to Jacobian of u comma v with respect to x comma y, which is equal to, so here ux u y v x, this is v y. So first we have to find ux. So how to find partial derivative of u with respect to x? 1. Partial derivative of u with respect to y is 1. Partial derivative of v with respect to x is 2. Partial derivative of v with respect to y is 2. Therefore, the Jacobian equal to Jacobian of u comma v with respect to x comma y, which is equal to, so here which is equal to determinant ux is 1, uy is 1. So here ux is 1 and uy is 1. Ux and uy and vx is 2 and vy is 2. So therefore here vx is 2 and vy is 2, which is equal to, so determinant is 2 minus 2, which is equal to 0. Therefore just we can observe one thing. Here this function is equal to x plus y and v of x comma y equal to 2x plus 2y. So you can write 2 times x plus y. So here just observe one thing. So these functions are here u comma v are here according to, so this is equal to 0, are functionally dependent. Here functionally, here dependent, here functionally dependent. Just observe one thing. So this is okay, but just before that solving, so here u equal to, so here this is not the part, u of x comma y equal to x plus y and v of x comma y equal to here 2x plus 2y. So take 2 common, so this is equal to x plus y, which is equal to 2 times the value of x plus y is u. So here u of x plus y. Therefore u equal to 2 times v. So one vector, one function is multiple of other vector, other function. So therefore these two functions u and v are functionally dependent. So here this also, with the help of that definition of Jacobian, we can prove your function u of x comma y equal to x plus y and v of x comma y equal to 2x plus 2y are functionally dependent, because Jacobian is 0. So now I want to discuss, most of the time they will ask question. So check whether the given functions are functionally dependent or functionally independent. So here if the functions are functionally independent, that is here if Jacobian is non-zero, here if Jacobian is non-zero, here functionally independent. So here functionally independent, but if Jacobian equal to 0, functions are dependent. So at that time we have to find the relation between these two functions. So here this is my u is x plus y and this is my v equal to 2x plus 2y. So here according to this definition, u and v are functionally dependent. So here if this u and v are functionally dependent, so find the relation between u and v. So here u equal to x plus y and v equal to v of x comma y equal to 2x plus 2y. So here 2 times x, just take 2 common, x plus y, 2 times u of x comma y. Therefore u equal to 2 times v. So this is the relation between u and v. So here most of the time in exam they will ask, check whether the given function is functionally dependent or not. If dependent, find the relation between u and v. So here this is my relation between u and v with respect to this two function u comma v. Now in the same way I want to solve this 2-3 example so that you will get one idea. So I hope all of you understand what is meant by functional dependence and functional independence with respect to the definition of Jacobian. Now here this is my example 1. So here example 1 is about, so here example 1. So example 1, so here 1 equal to u equal to e to the power x sin y and v equal to e to the power x, this is cos y. Check u comma v are functionally dependent or independent. So here u is this, v is this, so u and v is the function of x comma y. Therefore I want to find Jacobian equal to Jacobian of u comma v with respect to x comma y, which is equal to, so here u with respect to x, u with respect to y, v with respect to y, x v with respect to y. Therefore ux, partial derivative of u with respect to x. So here sin y constant and partial derivative of u with respect to x is e to the power again x. So here partial derivative of u with respect to y, the derivative of sin y is cos y, therefore e to the power x, this is cos y. Now partial derivative of v with respect to x. So here derivative of e power x is e power x, so this is e power x and this is cos y, and partial derivative of v with respect to y, partial derivative of v with respect to y, derivative of cos y is minus sin y, so here this is minus times e to the power x, this is sin y. Therefore Jacobian equal to Jacobian of u comma v with respect to x comma y, which is equal to, so here ux is e power sin y and uy is e power x cos y, vx is e power x cos y, vy is minus e power x, this is sin y. Now take the determinant of this thing. So here e power x sin y minus e power x, so here this is minus e power 2x, this is sin square y, this is minus e power x, this is e power 2x, this is cos square y, which is equal to, here minus I will take minus common, e power 2x common, this is sin square y plus cos square y, which is equal to minus e power 2x, this is 1, which is equal to minus e power 2x, which is never 0. So exponential functions are never 0, this is not 0 for all x. So here therefore Jacobian is non-zero. When Jacobian is non-zero, at that time your functions are linearly when your Jacobian is non-zero, at that time functions are functionally independent. Therefore u comma v are functionally independent. Functionally independent. So here this is about example 1. Now I want to find example number 2. So here I want to check the example number 2. So please pause and write. Now so here example 2 given thing u equal to x minus y by x plus y and v equal to x plus y by, this is x. So here this is the given thing. I want to check u and v, my u of x comma y equal to this and v of x comma y equal to this. I want to check my function u comma v are functionally dependent or functionally independent. Now for that purpose I want to find the Jacobian, which is equal to Jacobian of u comma v with respect to x comma y, which is equal to, so here partial derivative of u with respect to x, u with respect to y, v with respect to x, v with respect to y. So here u x, which is equal to, so here I want to find the partial derivative of this function with respect to x. So here this is the product of two functions f and g. Derivative of product quotient of two function is g as it is derivative of f minus f as it is derivative of g divided by quotient square. Therefore here x plus y as it is derivative of numerator 1 minus x minus y as it is derivative of denominator is 1 divided by x plus y whole square, which is equal to, so here this is x plus y, this is minus x plus y whole divided by x plus y whole square, which is equal to, so here x gets cancelled, this is 2y by x plus y whole square. Now I want to find uy, so here uy equal to, so here in the same way, denominator as it is, x plus y as it is, derivative of numerator with respect to y. So here derivative of x minus y with respect to y is minus 1 minus x minus y as it is into derivative of denominator with respect to y, that is x plus y with respect to y is 1 whole divided by x plus y whole square, which is equal to, so here just multiply minus sign, so this is minus x, this is minus y, and so here this is minus x, this is minus minus plus y divided by x plus y whole square, which is equal to, so here this is plus y and minus y gets cancelled, this is minus 2x by x plus y by whole square. So this is my partial derivative of u with respect to y. So here I want to find partial derivative of v with respect to x. So here partial derivative of v with respect to x, I want to write, so v equal to, so here 1 plus y by x. So partial derivative of v with respect to y, derivative of 1 with respect to x is 0 and derivative of y by x is, here this is minus y by x square, simple, and partial derivative of v with respect to y, this is simple, 1 by x. So here 0 plus 1 by x. Now therefore Jacobian equal to Jacobian of u, partial derivative of u comma v with respect to x comma y equal to, so here determinant, so here ux is 2y by, here this is x plus y whole square, ux this is uy minus 2x by x plus y whole square, vx minus y by x square, and vy 1 by x. Now take multiplication, which is equal to 2y by x plus y whole square into 1 by x minus, here this minus and this minus minus becomes plus, so this is minus last, divided by x plus y whole square into, this is y by x square. So here which is equal to, so which is equal to just 1x and 1x gets cancelled, this is 2y by x into x plus y whole square minus 2y by x plus y by whole square. So here this is same quantity, this is same positive negative, which is equal to 0. Therefore here Jacobian is here, therefore Jacobian is 0. This implies that u comma v are functionally dependent as a function. Therefore u comma v are functionally dependent. If u comma v are functionally dependent, so now we have to find the relation between u comma v. So here now I want to find the relation between u comma v. How to find is the following. Now so here from this we can say, here they are directly saying u and v are functionally dependent. If they are dependent, that is one function is the multiple of other. So how to find the relation between two functions u and v? So here u is this, so here u equal to x minus y by x plus y and v equal to x plus y by x. So here u into v, we can write u into v, this is x minus y by x plus y into v, that is x plus y by x. So here this cancel with this, which is equal to x minus y by x, which is equal to, now so which is equal to x minus y by x. Therefore so here 1 minus y by x, so which is equal to, just add here, add 1. So here I want to, this is 1 minus, so here here plus add and minus 1 minus y by x. So here this is 1 as it is, here I am adding plus 1 and subtracting minus 1. So 1 minus 1 becomes 0. This is my y by x, which is equal to, so here 1 plus 1 is 2, so this is minus 1. So here I want to write minus 1 minus y by x, which is equal to 2 times. So here minus x minus y. So here I want to multiply just here. This is 2 times. So here minus x minus y divided by x, which is equal to 2 times. This I will take minus sign common. Here x plus y by x, which is equal to 2 times here minus. So here x plus y by x is v. So this is my v. Therefore u v equal to this. Therefore u equal to 2 minus v by v. So therefore, so this is the relation. So here u equal to 2 minus v by v. So this is the relation between u and v as a function. So with respect to this function, u equal to x minus y by x plus y, v equal to x plus y by x. So just observe one thing. Here is the key idea. 1 minus y by x. So here 1 minus y by x as it is. So here I am adding 1 and subtracting 1. So here I am adding 1 and subtracting 1. So here this 1 plus 1 left to right. So 1 plus 1 is 2. So this minus 1. This is minus y by x. So here this is equal to 2 minus. So here minus x minus y by x. Here I am solving this step. So after that 2 minus, here I want to take minus sign common from this 2. So minus x plus y by x, which is equal to 2 minus, so x plus y by x. So x plus y by x is the value of v. So 2 minus v. Therefore u v equal to 2 minus v. U equal to 2 minus v by v. This is my relation between function u comma v, because they are functionally dependent. So here this is the relation. Now I want to define. So I want to check example number 3. So here u equal to this, v equal to this, and w equal to this. As u, v, w are functionally dependent or independent. So here please pause and write. So here now example 3 says, so here if u equal to, so here given information x y plus y z plus x z and v equal to, so here x square plus y square plus z square and w equal to x plus y plus z. So this is my function. U of x comma y comma z is this, v of x comma y comma z is this, and w of x comma y comma z is this. This is divided by in terms of x y z variable. Now I want to check whether the functions u, v, w are functionally dependent or functionally independent. So here for that purpose I want to find the Jacobian. So Jacobian of u comma v comma w with respect to here with respect to x comma y comma z, which is equal to, so here first row is related to u, x, u, y, u, z. So here u, x, u, y, u, z. Second row is related to vx, vy, vz. So here this is vx, this is vy, and this is vz. Now third row, this is wx, this is wy, this is wz. So here this is my Jacobian in 3 variable x, y, z with respect to 3 function u, v and w. So here which is, now I want to find ux. So here partial derivative of u with respect to x. So here x is there, so therefore this is y plus, so complete term is constant, so 0 plus this is z. So here this is my partial derivative of u with respect to x. I want to find partial derivative of u with respect to y. So here partial derivative of u with respect to y. So here y is there. So derivative of y with respect to y is 1. This is x. So here derivative of yz. So derivative of y with respect to y is 1. This is here z, and here there is no term y. So complete term is constant. So derivative of constant is 0. So here now partial derivative of u with respect to z. So here there is no term z. So this complete term is constant and derivative of constant is 0. Now come to here, z is there. So derivative of z with respect to z is 1, and this is my y plus this is x. So here this is ux, uy and uz. Now I want to find Vx. So here Vx. In the same way, here while finding partial derivative with respect to x, these two are constant. This is 2x. Here Vy is 2y. Here Vz is 2z. Now Wx. So here partial derivative of w with respect to x is 1. Partial derivative of w with respect to y is 1. Partial derivative of w with respect to z is again 1. So therefore Jacobian equal to the partial derivative of u comma v comma w with respect to x comma y comma z, which is equal to determinant. So here ux is y plus z, uy is x plus z, uz is y plus x, and vx, this is vx is 2x, vy is 2y, vz is 2z, and wx is 1 1 1. So here which is equal to, now I want to check whether this determinant is 0 or not. So here which is equal to, so here y plus z times, so here 2y minus 2z. So here first as it is, here head this first row and first column, 2y minus 2z minus x plus z. So here minus x plus z. So here this is bracket minus x plus z times. So here 2x minus 2z, 2x minus 2z plus y plus x times. So here 2x minus 2y. So this is 2x minus 2y. Therefore which is equal to, so here this is y plus z complete bracket, here y plus z into 2y minus here y plus z into 2z. This is minus sign. So here minus sign, here x plus z into 2x minus minus plus x plus z into 2z. Now last here plus, this is y plus x into 2x minus y plus x into 2y. So here which is equal to, so here just multiply this. This is 2y square minus 2, sorry, plus 2yz. So here 2y square plus 2yz minus, so here 2yz. So this is minus 2yz. So this is minus 2yz. Here minus 2z square. So here minus 2yz minus 2z square. This is minus 2x square minus 2xz. Now here this is plus 2xz plus 2z square. Now come to here, this is plus 2xy plus 2x square minus 2y square. So minus 2y square minus 2xy. So just observe one thing. So here this is plus 2yz, cancel with minus 2yz. So this is minus 2z square. So here this is minus 2z square, cancel with plus 2z square. This is minus 2xz, cancel with plus 2xz. So this is minus plus 2xy, cancel with minus 2xy. So this is minus 2y square, cancel with plus 2y square, and this is plus 2x square is cancelled with minus 2x square. So therefore this complete term is 0. If here, now you know, if Jacobian is 0, at that time functions u, v, w in xyz variable are functionally dependent. Therefore u, v, w are functionally dependent function, are functionally dependent. So here this is the example. Now I want to find the relation between u, v and w. So here I want to find the relation between u, v and w. So here how to find is the following. Now so here w equal to x plus y plus z. So this is given. So here if w equal to x plus y plus z is given, therefore w square equal to, so here x plus y plus z whole square, which is equal to, so here x plus y plus z into x plus y plus z, which is equal to, so here x square plus xy plus xz plus here yx plus y square plus yz plus zx plus zy plus z square. Therefore, here x square plus y square plus z square plus xy, this is 1xy, this is 1xy plus 2 times xy plus xz. So here xz, so this is xz, so here 2 times xz, so this is yz and this is yz, so 2 times yz. Therefore, here x square plus y square plus z square is v. Here I will take 2 common, so this is xy plus yz plus xz. Here v plus 2 times, so this is my u, so this is my u, so therefore w square equal to v plus 2 times u is the relation between functions u, v and w. So here u is equal to this, v equal to this, w equal to this. So here as a functions u, v, w are functionally dependent. If they are dependent, we have to find the relation between these three functions u, v, w. So here according to this relation, w square equal to v plus 2 times u. So with respect to this relation, these functions u, v, w are functionally dependent. So this is the complete summary, and this is the complete concept of functional dependence and functional independence of the function. So keep in mind, determinant is 0. For example, for any matrix, determinant is 0. At that time, these vectors are linearly dependent in the given matrix. If the determinant is 0, vectors are linearly dependent. In the same way, if the Jacobian is 0, Jacobian is determined by determinant. If Jacobian is 0, functions are functionally dependent. And matrix determinant is non-zero. At that time, we can say if the rank of the matrix is full, means each and every vector. For example, A is the matrix of order m cross m, and rank of your matrix is m. At that time, we can say m row in my matrix are linearly independent. So here m linearly independent row are present in my matrix, means m linearly independent directions are present in my. So here we can say m linearly independent vector are present in my matrix. So in the same way, linearly independent vector is related to functionally independent function. Linearly dependent vector is related to functionally dependent functions. So here this is functionally dependent vector, functionally dependent vector, functionally independent and functionally independent vector. So here if vectors are linearly dependent, that is one vector is the multiple of other. So this is the relation. In the same way, if functions are functionally dependent, so we have to find the relation between your function u, v, w or u, v, whatever may be. So in this way we can solve any example. So maybe they will ask in the exam. So in any kind of exam, engineering or anywhere, they will ask, check whether the given functions are functionally dependent or not. If dependent, find the relation between them. So in this way you can solve. So thank you.